Boa tarde a todos. Como nosso apresentador agora do seminário de encerramento da VI Escola de Verão de Curitiba é um apresentador estrangeiro, então eu vou falar em inglês e espero que todos compreendam, né? Qualquer coisa eu posso depois fazer alguma tradução se for necessário. I am really pleased to have all you here in the ending session of our renowned Professor Jürgen Kurths from Germany with us. I will give a small introduction. Of course, his curriculum it is quite extensive, but Professor Jürgen Kurths is a distinguished German scientist known for his groundbreaking contributions in the fields of nonlinear dynamics, complex systems, and network theory. His research explores the underlying patterns and the behavior in complex systems across various disciplines, from physics to biology and social science. He is professor at the Humboldt University of Berlin, and a key figure in the Institute of Complex Systems at the Potsdam Institute for Climate Impact Research. He is known to be editor-in-chief of Chaos Journal and many other journals that he's also contribute. He has a H factor larger than 100, more than 1,000 papers published, more than 100,000 citations. And of course, it is really a pleasure to have him with us today to do this ending session. So thank you very much, Professor Jürgen.
Yes. How to take? So, is it okay? And they also hear via microphone? No. Okay, also for the people here. Okay, yeah. Hello, everyone. I'm very happy to be here. And I'm really astonished. Friday afternoon, all students are sitting here. In Germany, it would not happen. We would go for a bar or football or whatever, soccer. That's really, I hope I can enjoy you a bit and that you will not be angry with me spending the time. I was told that you heard already about fractals and chaos. And now we would consider the case when you have such systems which are chaotic or fractal, are coupled, put together in some way. What happens then? And the basic phenomena is synchronization, in this case. And this is the main topic of my talk. Very simple. This is a house where I had my office. I had now to change a bit. And in this house, in this cellar here, this guy Michelson, which you all know, I hope, made experiments in more than 100 years ago, 140 years ago. And it's a really very nice place, very nice campus. Several of you were there, and I hope you all enjoyed the campus, maybe also a bit working with me. So outline first some introduction. Then I will give two kinds of synchronization and then go always a bit illustrated with applications, which we did and others, and then go to another kind of coupling. This is then even complex networks, as a larger number of systems and applications to climate. So the basic is synchronization. This is a very well-known term. You all know, have heard and use this, but in a maybe a different context. This is a Greek writing of this, the origin, and in the literal meaning, in the original meaning, it means sharing a common property in time. And I will mainly talk about phase synchronization, and this is very close to this very original old meaning. And you have heard about nonlinear sciences, complex systems, and many people think it's a new discipline. It is not. It started in 1665. Not so young. Do you agree? Astronomy is older, mathematics is older, but machine learning is a bit younger. And this was done a work by Christian Huygens, who discovered phase synchronization and called it that time sympathy, which I like a lot, this word. And this is Christian Huygens. And what he did was, maybe let me start with this. That time he played a lot with pendulum clocks. Pendulum clocks, you know, yeah, these guys making click, click, click. And then, yeah, but this is important because he was ill at home. There were several clocks hanging, and then he saw two such clocks made this click at the same time. And then he became awake, and then he invented perturbation theory, if you wish. That means he stopped both pendula, let them start at arbitrary positions. And he found then that after a short time, this comes again to this sympathy. Again, this click at the same time. And then this was that he found that it's a robust phenomenon, we would say, or stable phenomenon. And then he also understood the mechanism. And the mechanism is due to the motion of the beam where both clocks were hanging, because he lived in a half timber house, such examples. Not this, but only to give you an example. And such a half timber house has wooden beams, and this is a skeleton. You can take away the stones, it will stay, the house. It's really the stable thing. And two such pendulum clocks were hanging at the same wooden beam. And this interaction through the wooden beam was enough. Here you would not find it. This is no interaction. This is too stiff. And this was then also his luck that he lived in a half timber house. He found this phenomenon, and he also used this then for constructing clocks with high precision on boats and ships. This was a very hot topic that time. You can tell me, okay, this is old stuff, 1665. Why is this guy talking about this? Let me give one example, more modern. In the year 2000, there was an opening of the so-called Millennium Bridge, 2000 Millennium Bridge in London. A small bridge, only 300 meters, is nothing, connecting St. Paul's Cathedral and Tate Modern Gallery. And I show you now, I hope it works. No, it works. Now I show you. Is it working? No? Ah, yeah. So this is a movie of the opening. It was sunny day, which is not so typical in London, but that day was sunny. And people went then on the bridge. You see, we're happy, nice bridge, we can go there. Now look to the bridge. Do you see? And now see, observe also the people. They do not go longer independently, but as people on boat. You see? This was a few years ago. This is a modern Tate. Okay. The question was then what happens there? Of course, all such large mechanical systems have unstable modes. That's known, and engineers know how to treat them. But usually these unstable nodes are in vertical directions, and this is what they treat. But here, due to the special construction, there are also extremely strong unstable lateral modes, and this they have not considered. And one can bring this back to a more academic in some so-called phase equations and find then that this is a so-called Kuramoto synchronization transition. Kuramoto is a famous scientist in complex system science. He will get the Boltzmann medal this year. And he described this already in 1984. But the engineers were not told about, were not taught about. And the crucial point is here, the coupling means when there are sufficiently many people, when there are sufficiently many subsystems on the bridge, then we are beyond the threshold and synchronization sets in. They made then experiments and let more and more people go. What can they do? They do not have students. We have students. We can make experiments with students. They do not have this, but they have workers. They let more and more workers going. And indeed, when a certain number of workers were on the bridge, it sets in. Very interesting thing. But now you can go because a German company came, brought dampers, and now is stabilized. And it's no longer a problem. As you see, it's indeed also these days a problem, synchronization. And you have examples in many things. The Mexican wave, you are here all soccer fans. This is also called Mexican wave here, or Brazilian wave, I do not know. Ola, okay. Okay. You have then fireflies in Southeast Asia. They also are lightning in synchrony. And a very interesting thing is with organ pipes. They are never identical, of course, are always different. But even if they are different, Lord Rayleigh, this famous guy, found then you can have two synchronization effects. Either quenching, that means no sound, or maybe playing in unison. And we have an organ manufacturer in Potsdam. I asked then the master, do you know this effect? He told me, yes, he knows both. This playing in unison is very often. Quenching, he has found only a very few times, but he has his tricks how to avoid this. It's really interesting things. And then, yeah, let me, and you have this, of course, in physiology, the neurons, any actions we are doing, for this it's necessary that several neurons fire in synchrony, fire at the same time. And this is a typical example. This is necessary for any action, but if the synchrony is too widespreading, then you have strong disease as epilepsy or Parkinson. And then also one can control the breathing. This is easy. And therefore, you can also control with this the heart rhythm. This is what yoga are doing. And many other examples. So what is necessary for synchronization? When can we expect? You have to have at least two systems. We call it oscillators. That's the best case. You can also have one master, also one driver, and one slave who will be driven. And what is very important, they should be different in some property, maybe in the initial condition, maybe in the internal frequency. And the idea of synchronization is that they become identical in the main property. As completely identical or adjusting their phases. And this was all known, all okay. But the question was and came up in the from the beginning of 80s when people studied chaotic systems. Can we also find synchronization in chaotic systems, in coupled chaotic systems? And this was really the first study on this and the first successful studies in Japan, 1983. And they found that really two systems, when they are identical to chaotic system but have different initial conditions, due to coupling, they become identical, remain chaotic. This was then also later found by Pecora and Carroll, but this was really the original paper. Then there is some generalized synchronization where you have a driver and a slave. And we thought a little later, maybe one can also consider only the phases. As in the Huygens examples, only the phase, the motion of the pendulum. And we found then indeed that also for chaotic systems, when they are coupled, the phase can become synchronized, but the amplitude must not. As it's not so easy to see. This is if you take this. As that means we are interested in phase synchronization. Phase you all know, yeah? Also the definition of phase of an oscillator. You have not to go to the wall and show me, only say yes or no. And what is a typical property of the phase? During one oscillation, it has an increase of 2 pi because it makes a full round. And the increase is linear. But main point is 2 pi increase. But how to define a phase for a chaotic system, which is not simply periodic? This was a main problem. Also here in the periodic, we have a linear increase. Omega is a frequency, t is a time. And we have an increase of 2 pi per period. And also the derivative of the phase is a frequency. This is all, I hope it's all known. This is classic. So how to generalize this? And for this, we used a technique proposed by Dennis Gabor. He is, by the way, the only engineer who got the Nobel Prize in physics for holography. And for holography, he needed strongly this definition of phase. And now it's also a bit more open. These days, also machine learning people can get. And what his idea was to extend a signal, a real signal, also real value signal S of t, to the imaginary plane. And he showed that the imaginary part, this one, S tilde, can be calculated via the Hilbert transform. Maybe you have heard, if not, it's not so important, but this is a classic transform. It's not so known as a Fourier, but also rather well-known Hilbert transform. Decomposition in amplitude, A plus e to the power j phi. And you have the phase phi. And the good thing is that you have here really the time dependence of the amplitude and of the phase. And for rather general signals. Then one can also have a bit direct definitions, but let me go a bit away from this. First, to show how the Hilbert transform is working. Also, let's have first such a signal which is periodic but damped in amplitude. Then you get indeed for the amplitude, for this A of t, you get the envelope, this one. And for the phase, I give you now the derivative, you get 1. This is a frequency, yes. So this is for the simplest case. Now a bit more difficult case that you have not only changing the amplitude, but also the frequency. The period is becoming longer and longer, you see. And indeed, this Hilbert transform gives also that this frequency is becoming smaller. Also it works also in this case. And for a chaotic signal, we have here the so-called Rösler attractor Rösler system, a chaotic system. This is the X component, the 3-dimensional, and we get here also the envelope, which is much more complex for this, and can estimate then also the phase. And here it looks at the first view, it is increasing linearly. Yeah, what you say? But now let's subtract this linear part, this mean frequency multiplied by time. Then you see you get this one. Also there is really rather strong fluctuations around this linear increase. That means the phase has really a more complex dynamics, and we can retrieve this via this Hilbert. This I will not go to too many details. Let me show how it works. First, this is here our Rösler system. This is a nonlinear system, has a nonlinearity only here, xz. All other is linear. And this is a chaotic, and with a mean frequency. The mean frequency is omega. And now we drive this system with a periodic force, and the frequency now, capital omega, is a bit different from this omega. And the question is, can we have, due to this driving, a change of the phases and the frequency? And this is indeed the case that we can get synchronization, that we really can get a shift of the forced system, of the whole system, compared to the original one. And we can also estimate for which amplitudes of E and which differences capital omega minus small omega, we can reach this synchronization. And this is this case periodic driving. But more interesting is to have two coupled chaotic systems. Here we have two Rösler systems, they are coupled here only in the X component, symmetrically coupled. C is the coupling strength, and omega 1, omega 2 are the internal frequencies, different. And we start with a bit different frequencies, a few percent different, and for different coupling strengths. When the coupling string is very small, then the phase now really is increasing, no synchronization. When we go to 0.03, then you see some different behavior. You have a plateau, short increase, another plateau, and so on. And all people who are familiar a bit with complex system know that this is at the borderline of something. This is very typical, such transient behavior. And indeed, if we now increase a bit more the coupling, the phase difference becomes almost zero. That means here we reach phase synchronization, and when you compare both amplitudes, they are not synchronized. They're almost uncoupled. And this is a speciality. Okay, but this is a main phenomenon. So far, so clear? So now one can think, okay, let's apply to data. We have now our technique where we can calculate a phase, and then we see whether it's vanishing or not. But as usually, life is not so easy. We have, one can also make reduce and can calculate for which coupling strengths you can get this synchronization. But as I mentioned, life is not so easy. For instance, when we go to another famous system, Lorentz system, also chaotic one. Here we have two nonlinearities, xz and xy, and we force it, then we never reach such a plateau. That means this would be phase synchronization. We always have some differences. We were a bit astonished about what happens, but this has to do because there are so many short time periodic behavior in the Lorentz system with a lot of frequencies, and one cannot catch or lock all the frequencies. And therefore, you have then such a behavior, what we saw before in some sense, and we have a plateau, but then a jump, another plateau, etc. And even if we increase the coupling more and more, this will not vanish. This is intrinsic. And that means you have such phase jumps of 2 pi, can be also 4 pi also. This is one problem with phase jumps, and you also have phase jumps when you have chaotic systems added by some noise. Then you also have such phase jumps. It's unavoidable. And there are several reasons for these phase jumps, and therefore we have to avoid this for data analysis. And that means we do not consider the difference. This NM means that it's not only it's not 1-to-1 synchronization, but can have 1-to-2 or so. And we consider only the so-called wrapped phase difference. That means only in the interval 0 to pi. We always subtract then the larger parts, and this means we this way we filter out such phase jumps. And then one can really use this method. For instance, here, this is only non-phase synchronized case. And when you have now the distributions of these phase differences, it's almost uniformly no special structure. But here, looks not so different, this one and this one, I would say. Here is clear, this is very bounded. But here, if we now filter out the phase jumps, we get a very strong unimodal map, and this is then a clear indication for phase synchronization in a statistical sense. In the real world, you often have to use statistics. You cannot only use equations simply, and differences also. You should think which kind of which role noise could play and could destroy, or maybe even construct some phenomena. Then one can also have some criteria to see whether this kind of behavior is significant or not. One can construct some tests. This is here, and they are working. So now my question is synchronization good or not good? I have not to ask you the question because the answer is already written here. It's context dependent. As I mentioned already, when you have very strong synchronization in the brain, then you have some disease, epilepsy, Parkinson or so. But without synchronization, we could not survive. And here are some applications. First, it was important to have in lab experiments. One starts with electronic circuits, with plasma tube, with lasers, electrochemistry, and many others. And this is, you can, in the lab, you can control the experiment. But in real life, you cannot control completely. But one can also show that the cardiorespiratory system, also breathing and activity of the heart, are also synchronized. Or in Parkinson, epilepsy, and then one maybe interesting point, we did not do this analysis, was double tennis. People analyzed the motion of tennis player in double tennis, and they found out if one team is moving in phase synchrony, they are much more efficient than the other one. I do not know whether it's true, but I'm not a tennis player, but it's interesting, I think. So I give you a few examples. One is so-called posture control. That means you have to stand on a plate and stand quiet. Do you think it's an easy task? Easy cognitive task? It's very, very hard. You cannot, even the well-trained people cannot do it longer than 2 minutes or so. Then they start moving. But the question is now, and here is measured in both X and Y direction when you make some shaking, also small ones. Here is the small ones during the stationary phase. And how are they doing? And the task was here to do this with open eyes and with closed eyes, and to see some difference. And you had healthy and non-healthy people, which has some brain disease. And we made then face, here are the data, which looks very similar, I would say. But here you see a very strong face synchronization. Here you do not see it. And here is also, and here this is eyes closed, when the eyes are closed. And this is especially for a guy who has some disease. And this disease means, or let me say with healthy people, we are able, I hope I'm also healthy, we are able to control it a bit independently, this X and Y direction. But some non-healthy people cannot, and therefore they have to synchronize. And this could be a simple test whether you have something, and before going to deep analysis. This is one. Another one is with the cardiovascular system. This is also a bit special. You have here this ECG, the heart rate, so-called the R peak, so-called R peak is the most pronounced. And very often one looks, calculate only the difference between these different R peaks. But this is a more point-wise signal. Breathing is very continuous. And how to combine both, that was a bit a question. And for this, we developed some tool which we call Synchrogram, where we have here the time, and then we consider, we use this as an advantage, because here one can calculate the phase, continuous signal. And then we consider what is the phase when an R peak occurs. Here's the next, which phase are we here and which phase are we here? And this is put together here. These are these different phases during 2 respiratory cycles. And you see here after about, this is here 10 minutes, yeah, 600 about, you see that you have now a stripe-like behavior, 6 stripes, which is a clear indication for synchronization. This is 2 respiratory cycles, 6 heartbeats, that means 3-to-1 synchronization. And this was for some sport people which were at rest. Also one can find this also there. And the question is then also, is this synchronization, what is by chance, or because we cannot control the system. You cannot give them electricity, or you should not. You can, of course, but you should not. But we are very dynamic. and therefore you get a lot of perturbations. When I'm talking, I perturb you. You cannot relax so much. And then you have some changes in this, typically in the heartbeat. And the point is now, this is also some so-called passive experiment, if you wish. You get some perturbation naturally, and whether you come back to this synchronization, and this is indeed the case here, you had some perturbation, and you really come after a short while back to synchronization. And this means it is a real phenomenon. As with lasers, one can change different parameters, but here is this. One can also study this during sleep, and then it turns out that you have, especially in the non-REM phase, REM means rapid eye motion when you have not deep sleep, but in the deep sleep, you have typically synchronization, well-expressed synchronization. Another problem is with mother-fetus system, because this is really a strong danger for women when they have so-called preeclampsia, then they can die. And it's very hard to early recognize that something with the heart system is not working. And to measure the heart variability of the mother is easy, but of the fetus, of course, not so easy. You cannot go inside. But what is in direct option is with so-called magnetocardiography. As you measure the magnetic field. It looks very terrible, but it's not. It's without, you have not to go in the body or so, it's unbloody. But of course, the device is not so easy. And then you can also calculate the cardiac activity of the mother. And we analyzed such things and found that there is also in the health, if both are healthy, then you have epochs. This is not for a long time, all is very dynamic, but you have epochs, these black dots, where you have such synchronization. And we made then also an experiment. We let the women, the mother, breathe in a certain speed. This was in different speeds, and then it turns out with some pause in between that when they are in some special speeds, then you get very most expressed synchronization. So maybe I will skip this a bit. Let's come now. Very often you have not only two systems, coupled system, as mother fetus or heart and breathing, but very often, especially in the brain, you have many actors. And what you can measure, there are several options. The most classic one is so-called EEG. You measure the electric activity of the brain. And here in this case is with 30 channels, with good enough resolution and time. And now the people have to get, in order to understand something, a simple task. This is very difficult. We are always doing a lot of things, but to have a simple task that you can refer solving this task to the synchronization analysis. And one typical example, this is from cognitive psychology. They are really scientists. They are not only talking. And they have this so-called Kanitsa figure. That means you have here, you see immediately that this is a triangle. But when you look here, you do not see it immediately. Your brain has to process some time in order to identify, that's a triangle. And this is what we measured. We gave the persons a triangle at the computer, and then EEG was measured. And we made then synchronization analysis in order to understand what happens in the brain. And this is here, 0 means the presentation of Kanitsa. This was before presentation. This is, if you wish, some quiet brain, as quiet as it can be. Then it remains quiet even after the presentation. Only after about 150 milliseconds, you see some activity synchronized. And then it becomes more and more expressed, and about 300 milliseconds, so 0.3 seconds after presentation, recognized. And then the good thing of our brain is that it can switch off. It's done, And you see this also here from the synchronization. It goes down and then it's over. And here is really the advantage, which areas of the brain are responsible for this processing. This is some visual processing, and this fits with the general picture, but here one can really get it out in some detail. So then maybe there are also artifacts as typically, and very often it's important to have some decorrelation in order to avoid problems. So maybe because I would like to go to the climate also. We have also some more difficult cases when we cannot use the direct phase definition, but we have to use the derivative of the components, and then we can apply this also to more complex situations, as in system Earth. I think you already introduced complex system Earth, yeah, in some sense, yeah. And this is really, we have, it's a real complex system, let me say it this way. And we have then some typical oscillations, so-called North Atlantic oscillations. They look this way, but this is not nice, this is too noisy. And it's a serious discussion which structure is behind. Therefore, this is nothing for us, it's too difficult. But what we are interested are monsoon data. Indian monsoon. We have here also now monsoon, but in India is much better to see because the rain is more organized, let me say. And this is here then the monsoon. Of course, every year the monsoon comes. This is Indian going back to 1880, but the intensity varies strongly. Here you see it's a very weak monsoon, very strong monsoon. And the question is then, what is the interrelation of monsoon with another phenomenon, which you know very well? This is El Nino. Has this an influence on the Indian monsoon? This was the question. A lot of work about done with classic methods, but no real result. And then we thought, okay, let's look for this. And we really analyzed the data. This is here the Nino data, which looks, this is a bit filtered, which looks oscillatory. These are all India rainfall data, very noisy. As we have to make some filtering. This we did. After filtering, we have this signal and this signal. And now we made synchronization analysis. But the system Earth is very dynamic. Therefore, you cannot do it over all the years. We tried, but we saw nothing. But in windows, and then see, is there something in this window? Is there in the other window? What can we see? And this is here the main result. This looks a bit strange, but it is not so strange. But here again, we have time. Here's a phase difference between both. And you see now, in general, is a decrease of the phase difference over this more than 100 years. But if you look a bit more carefully, you see here is a plateau, and here is another plateau. Also this is around 1900, and here 1964 till 1980. Yeah, I have some. Is it my? Yeah. Okay. Thank you. And this is then an indication. This could be an indication of phase synchronization over 20 years. But this was a bit too hypothetically. Of course, we made statistical tests, but we applied then also other methods. Wavelet analysis, we found the same. This is some decomposition into frequencies. And one can, this is a cross wavelet. You can compare two different kinds. And then also we made this Granger causality, but a nonlinear Granger causality, and found also all what were more or less in agreement with the periods of phase synchronization. But then the question is, why these two epochs only show phase synchronization? And then we talked with a lot of climatologists who should know. No answer. No one had an idea. But one came and then, please look for volcanic activity. We looked, And indeed, here, shortly before the onset of this, was a strong eruption in this, I think, Philippine, and here another one. And this was, we published this in 2005, and we could write only as hypothesis, because only 2 events, you cannot make a test. This was a bit not so satisfying, but you know, scientists are a bit strange, and we never forgot about and found them good partners in India. They have a lot of data, a lot of models, also from other volcanic activities from the past data and so. And then we really could show with several examples that this is indeed a significant indication that volcanic activity, if strong enough and at the right position, not activity here or so, can induce such a phase synchronization. And this we published in 2020. That means 15 years later. This is, you have to know this. Yeah? You are young, but sometimes you need a long breeze. You cannot make it during one PhD, but finally we were successful. So now I have a bit more time, I hope. Okay, then let me go shortly to another kind of synchronization. This is what we call event synchronization. Also very simple thing, and this is now mainly for rainfall. Again, for such not continuous aspects, but strong events, even extreme events maybe. And this is here rainfall at one position, as one region. This is at another one. And then all what is above this is considered as a strong rainfall event here in this region A, in region B. And now the crucial point is to compare both. And you see that here, this extreme event or very strong event happens almost at the same time. Here the same, here the same. And if this happens not only once, this agreement, but significantly often, then we make a connection between A and B. And that means we have some synchronization in the rainfall. This is here again, and we construct a so-called complex network and try to analyze this. And this is also a bit our way of considering, especially extreme events or long-range connections. You have maybe heard about the Anthropocene, a lot of things happening, and we have so many extreme events. We have here now extreme in this area, I learned, and we applied this to rainfall especially. And the problem is, of course, network reconstruction. This we are doing via event synchronization. So now let me give one example from here, what we found. We studied the South American monsoon system. That means, what did I do? We took satellite data for rain, the so-called TRIM satellite, here is that time 14 years, with a good enough resolution. And only for the months December, January, February, when this is most expressed, this South American monsoon system. And we made then our very nice synchronization analysis. And what we found is the following. When you have here strong rainfall in this Montevideo, Buenos Aires area, then we followed up with this synchronization analysis that it goes this way, or better showing here, up to Bolivia, to the plateaus, to the high plateaus. Okay, but we could also do a bit more. This is here a bit better. And that means it has an average speed of 80 kilometers per hour. That means it needs 2 days to go from here to here. And this is very important for Bolivia to know such strong rainfall events, because they have a lot of effects, landslides, and so social effects. So with this analysis, we went to our friends. We had a large project with Brazil, to Marengo, Jose, I think you know him. And he looked at this. This cannot be. Rain comes in South America always from north to south, from Amazonia. This cannot be. And then my PhD student at that time, Niklas Börs, he looked for bugs and all things. No, was a really stable result. We again to Marengo. And then he understood these guys are not so simple to treat. Let me think. And then we really sit together and thought what could be the reason for this, because this is only a finding, one should have some reason. And then an idea came up that you have cold wind coming from the Antarctic, reaching this area, and is then like a carrier taking the precipitation northwards. And this was a general idea. Then we looked to the single events and found, I think that's given here, that in 60% of all such events, in 90 during El Nino, is exactly this scenario. And that means this is some kind of, has predictive power for such strong rainfall events. For here, we did then also a more general global analysis of rainfall of strong rainfall over the whole Earth, plus minus 60 degrees. And this was then published as the first paper on climate networks in Nature ever. We were very happy about. And here was also a very important problem, a methodological problem, so-called multiple comparison or multiple testing problem. We had to develop a special test of significance to identify the strongest things. And here, this is to give you the result. Here we have a lot of, or several nodes in the Himalaya, Tibet area, and looked for connections, synchronized connections to other areas. And this is after this correction. And you see there are really a lot of connections, of course, short range, but also long range connections. Then we tried what physicists like is some scaling. And as expected, when you have the distance between two nodes, the probability or the occurrence of synchronization is becoming weaker. That's clear. But then at some point, 2,500 kilometer distance, you have an increase again. This was first a bit unexpected, but if you think that a bit, then it's rather clear. This reflects more the thermodynamics, regional weather system, and here come the long-range teleconnections, especially Rossby waves, into the game, and they really increase then the synchronization, and one can then also show some further things, some Silk Road patterns, and so this really opens, in some sense, a new way of forecasting such strong events, and rather unexpected. Also here, the Rossby waves play an important role. This was not known as far we knew so far, that Rossby waves play such a role for strong precipitation events, because it's a different height. There are several kilometers between them. And this could be really open new ways for prediction. And maybe this paper's book, maybe I should go back if you would like to read the story in a more systematic way. This is the first part, then I recommend you our book. And a few perspectives let me give. One is to consider adaptive dynamic networks. That means so far I talked about this connectivity, it's also called topology, but also the dynamics, as the internal activity affects the topology very often, as in the brain, but also in climate. And that means one has to include models where the parameters are not only time dependent, they also depend on the system parameters, on the system state, excuse me, not parameter, on system state. And the other is what I also like a lot are so-called triadic motifs for network. Typically, you consider a motif as the basic parts of a network, and very typically you have triangles. That means you have here one node, here the other, here the third, and they are connected in this way. And now triadic means you have this one, and you have a third node, but this is not connected directly to a node, but modulates the interaction. And this really leads to completely different behavior, also for synchronization. And this is a very hot topic. We had last week a perspective paper in Nature Physics about, and this, if someone of you are interested, you are invited. A lot of work to do, and it's really very interesting, I would say. Okay, I think my time is over. I would like to finish, and please questions. Thank you very much.
So we have time for 2 or 3 questions.
Opinion formation is a typical example also of you. If someone of you would like to bring his opinion to all of you and will convince all of you, then it's not so easy. Yeah, he has. Yeah, please, please. That's a good point. That is one cannot say always that they share a common attractor. This is, of course, with all these examples in the beginning, yes, but you cannot say that the heart and the breathing has the same attractor. They are dynamically behave very similar, but you can also, we have also examples where the models are different, not only in the parameters, also in the structure. And you can get them also synchronization. And this is not necessary. And maybe for the neurons, many should have the same attractor, but when there are different types of neurons, I think then it's also a different attractor. But you can couple them and bring them together in the behavior. Never be synchronized, like other conditions that you can say, oh, never be synchronized. Yeah, but one can construct such things, but we have no clear criteria. We have criteria, synchronization is there, but to see from the equations whether they can be synchronized, in phase this is difficult. If you are going for complete synchronization, there that situation is much easier. Then one can say also they are able to synchronize or are unable. But with phase is a bit more tricky. And phase is more natural, let me say. Yeah. Okay. Okay, I'm coming down.
Thank you, Jürgen, for your excellent talk. It's always good to know the news about.
How do you know all this?
I would like just to add a little observation. When you gave us an example of phase synchronization in plasma, you mentioned Rosa. I would like to comment that Rosa, Epaminondas Rosa, was a professor here in Curitiba.
He was in Curitiba. This I didn't know. I know that he's Brazilian, but okay, yeah.
He was a professor here, and after he finished his PhD, he went to Maryland, and then he stayed in US. Now he works in Illinois.
Yeah, okay, that's. And also, when we are with Curitiba, I forgot to mention, also from the recurrence viewpoint, one can understand much better synchronization. And here are a lot of contributions. And will also come. Alice.
These relationships there between these three nodes you mentioned there in your. Could it be, for instance, apply to the case in which you have a change of teleconnection between 2 points caused by a different phase of, for instance, interdecadal oscillation or an interannual oscillation? I can give you an example. Madden Julian oscillation is intraseasonal oscillation.
Yeah.
And in certain phases, it really influences very much precipitation over South America. In, very important regions in Brazil as well. When you have an El Niño happening, the impact is much stronger. So you can even have very extreme events. So when something happens there in equatorial East Pacific, this relationship between MGO, convection, related convection, and rainfall or circulation perturbation over Brazil can be very strange.
Yeah. This is, also we are looking for a proof of an example in climate very strongly. And what we have, one thing, the simplest thing is what I mentioned, this with the Pacific and Indian monsoon or El Nino and the volcano, then this is really modulating the connection. But the other, what I have, and maybe this is closer to you, I told you yesterday we found teleconnection between Amazon and Tibet, and then we looked for influence of El Nino, exactly this kind. And that time it came out that during La Nina, this connection is much stronger than during El Nino. But this is preliminary, therefore but this could be also, thank you very much.
Might be, because you had El Nino or another even slower oscillation,
that's it.
Changes the basic state of the atmosphere in which the wave propagates. And so this can modulate the effect.
Yeah, this is really a very hot topic now. What we are looking.
The relationship between the Indian monsoon and El Nino, I would say, let me see, 3 decades ago, when I was in the US, a colleague of mine published a paper about this relationship between El Nino and Indian monsoon. During El Nino, Indian monsoon would be weaker. And well, at that time, in the interval, they analyzed it. It worked very well. It even made it to Nature. It was published. And but afterwards, this kind of relationship weakened and almost disappeared completely. It was not significant. And most probably there was influence of a longer multi-decadal oscillation in this relationship.
That's a very good point. Thank you.
Professor, thank you very much for the presentation. If I understand, the idea of motif is like you have a connection in 2 nodes, but you have another another node not connected with this one. So I want to know what is the difference in the motifs and the chimera stage, because the
chimera.
Yeah. Because I think if you have a chimera in the same network, but 2 states, different states, in this case we have to how to have chimera too.
Yeah, but all this chimera also is only considers connections between 2 nodes, pairwise connections. And this is here the difference. And this happens in chimera due to several reasons, that you have synchronized and non-synchronized in parallel. That's chimera. And but this happens for especially Kuramoto and other models only for pairwise connections in a whole network. They do not consider higher order connections. And this is the difference here, that this is so-called higher order connection. And when with social systems, you have a group, and when you are outside of the group, usually you do not touch one of the people, but the whole group in some sense, when you try to communicate with them. That's also a higher order connection. And this is a difference. It sounds first very similar, but it is not, mathematically and also from the phenomena.
Thank you very much. So I think we can thank our speaker again.
Yeah.
So I'm sure that everyone will
with you. Now I will start our ceremony of ending the summer school. I will speak quite fast, some short text that I have prepared here. So, ladies and gentlemen, on behalf of everyone involved, we extend our sincere gratitude for your presence and participation in today's event. We would like to particularly thank the Vice Director of Exact Science Sector, Professor Camila Carla Brites Queiroz Martins de Oliveira. Yes, it is a really big name. Also, in all sense, also the in exercise chief of physics department, Professor Alice Marlene Green, that received also some kind of prize in some sense because she completed the 50 years of as a professorship here in our university. The vice coordinator of the physics, 50 years as professor. Yes, first. Yes, sure. Yes, probably more will come, sure. The vice coordinator of the physics graduate program of our university, Professor Ginter Kellerman, and the coordinator of the sixth summer school of Curitiba, Emerson Cristiano Barbano. Additionally, I would like to express my sincere gratitude to all the sponsors of this esteemed event, as well as to the professors and students who have dedicated their time and energy to making this a reality. So thank you very much for everyone. Now I would like to say some small and brief words to pay a tribute for Professor Ricardo Viana. Professor Ricardo Viana also completed the 35 years as professor in our department. Yes, sure. Uh, Today we honor and express our deepest gratitude to a truly exceptional professor whose dedication and passion for teaching have shaped the lives of countless students over the past 35 years. Your unwavering commitment to education, your wisdom, and the inspiration you've provided to generations of learners are truly remarkable. Thank you for your outstanding contributions to the academic community and for the lasting impact you've made. Here's to your incredible journey and to many more years of success and fulfillment. Particularly, I was a student from Professor Viana, and several persons that are here also was students of him. And I'm not saying just by myself, and not also because I wrote here this, but everyone that I talked about Professor Viana has this same idea and this same feeling. Professor Ricardo Luiz Viana graduated in physics from our university in 85. His graduate studies were completed at Universidade de São Paulo, where he received the degrees of Master in Physics, Elementary Particles in that time, 87, and Doctor in Physics in Nuclear Physics in 91. In 97, he worked as a research scholar in the University of Maryland at College Park when he met Professor Jürgen Kurths, that is with us now, in the field of chaos theory. He works at our university since 89. where he is currently full professor in the Department of Physics. He created and headed a research group in plasma physics and nonlinear dynamics, which are his main fields of expertise. He published up to now 282 scientific articles. These numbers we need to take care because every day maybe more in international journals with more than 3,000 citations, H index 31. He is in the editorial board of the following journals: Journal of Applied Nonlinear Dynamics, Nonlinear Theory and its Applications, Fusion Plasma Physics, Frontiers in Computational Neuroscience, and Entropy. He is currently a member of the Advisory Committee on Physics and Astronomy of CNPq. So let's thanks Professor Viana. Now, I would like to, after this brief tribute, to call the Vice Director of Exact Science Sector, Professor Camila Carlos Brites Queiroz Martins de Oliveira, to give a speech. I am. Oh, but oh. So yes, but Professor Emerson could give a small gift for Professor Viana. Yes, excuse me because I am really bad with signals.
Muito obrigado.
No. That's next year.
Okay. Thank you very much. I am very moved by this tribute, and it has been a pleasure to work with you, especially my colleagues. And I am very honored to be here, and I hope that I will be ready for the next 35 years. Thank you very much.
Sure. Now I call Professor Camila, so thank you. I don't know by head. Yes, so thank you.
Oliveira, para aí. Bom, I'm going to talk in Portuguese, if you don't mind. Então, boa tarde. Eu gostaria, né, de agradecer vocês, a presença, né, como o professor disse no começo da palestra. Sexta-feira, carnaval já começou num monte de lugar e vocês estão aqui. Né? Isso já começa bom desse jeito, né? Vocês ainda estão aqui, apesar do carnaval já ter começado. Então, eu gostaria, né, em nome do setor de ciências exatas, de agradecer a vocês pela presença, né, agradecer à organização da escola, né, por ter organizado mais uma edição do evento da escola, que para o Departamento de Física, para o programa de pós-graduação em Física e para o setor de ciências exatas, né, já é um evento aguardado todo ano. Né, para os nossos estudantes e as nossas estudantes que são aqui, né, dos nossos cursos de Física, bacharelado, licenciatura e do programa de pós-graduação, a gente fica muito feliz de vocês terem vindo nas férias, e espero que vocês tenham participado. Para os estudantes e as estudantes que são, né, que vieram de outras instituições, a gente espera encontrar vocês aqui em breve, espero que vocês tenham sido bem acolhidos e bem acolhidas aqui. Vocês tiveram a oportunidade de ver só previamente o clima de Curitiba, porque teve sol, aí caiu uma tempestade que parecia, né, que o mundo ia acabar, e depois voltou o sol. Vocês não tiveram a chance de ver o tempo cair e despencar de uma vez e congelar todo mundo. Mas às vezes acontece. Então, mas eu espero, né, de verdade, que vocês tenham se sentido muito bem aqui nessa semana, tenham aproveitado todos os minicursos, todas as palestras que vocês assistiram, e que, sim, né, retornem para o nosso programa de pós-graduação em Física. Eu sou professora no Departamento de Física, então retornem, né, para o nosso programa de pós-graduação, e o setor de Ciências Exatas está à disposição de vocês para o que vocês precisarem, tá? Muito obrigada, bom retorno para quem vai retornar, bom carnaval para todo mundo, e até a próxima.
Bom, muito obrigado pelas palavras. Agora eu gostaria de passar a palavra para a professora Alice Marlene Green, que é agora a chefe em exercício do Departamento de Física.
Bom, boa tarde a todos. Foi sempre um prazer conviver com o professor Viana, que, além de ser um excelente cientista, excelente professor, sempre foi excelente colega, uma ótima pessoa. Eu acho que essa característica é também muito importante para criar um ambiente agradável dentro do departamento, ter um bom ambiente de trabalho. Meus parabéns, Viana, pelos seus mais de 35 anos de dedicação ao departamento e à universidade. Tá? E esperamos contar, né, com mais professores como você.
Obrigado.
Obrigada a todos pela presença aqui na Escola de Física, né, e espero que tenham tido proveito aí e tenham se divertido também, né, porque eu acho que atividades como essa devem ser prazerosas, nunca entediantes ou forçadas, ou enfim, algo que realmente dê prazer a vocês, né? Quando alguém não sente prazer com o que faz, tem que parar de fazer. E não ficar 50 anos insistindo, né? Se fica 50 anos insistindo, é porque realmente gosta do que faz, assim como os 35 dele. Então, tá bom. É isso aí.
Muito obrigado, professora Alice. Então, eu gostaria de chamar agora o vice-coordenador do programa de pós-graduação em Física aqui da Universidade Federal do Paraná, professor Günther Kellermann.
Obrigado, Tiago. Bom, eu estou substituindo o professor Renato, que não pôde vir, então, o professor Renato espera que eu fale alguma coisa inteligente para vocês. Pensei bastante e não encontrei nada muito inteligente para falar, né? Mas eu gostaria, na verdade, de agradecer, né, o comparecimento de todos vocês, né, para a escola. É muito bom para a gente ver, né, pessoas jovens, né, para continuar a carregar o piano, né, que a gente vai ficando velho, e assim é algo importante dos mais velhos, né, fazer, né, organizar esses eventos e dar oportunidade, né, para os jovens, né, conhecer, né, a ciência, né. Então, eu acho que a gente é bastante privilegiado nesse sentido, porque a gente faz coisas que gosta de fazer, né, fazer ciência é algo muito divertido, né. Eu acho que tem que ser divertido, como falou a professora Alice, e a gente, além disso, a gente é pago para isso, então é muito bom, né, ser... a gente tem que falar as coisas boas, né, para não desestimular, né, também uma carreira dura, né, a gente tem que trabalhar bastante, mas, de fato, assim, o pessoal está achando que eu sou novo, mas não sou não, tá? Já sou, eu lembro quando era estudante também, isso é a importância, né, dos eventos para a gente poder conhecer, né, ver o que é ciência. Então, eu também convido, né, a todos, né, que futuramente venham a fazer uma pós-graduação, né, na física, que considerem o nosso programa, né, a gente tem uma infraestrutura bastante boa aqui. Vocês vão poder obter todas as informações na página do departamento, né, tem informações sobre os pesquisadores, o contato com esses pesquisadores, as linhas de pesquisa, os laboratórios. Então, a gente está sempre tentando melhorar a página, né? E então, informações maiores vocês vão encontrar lá, tá? Bom, e dito isso, então eu vou finalizar aqui muito rapidamente, mas eu acho muito importante agradecer as pessoas, né, que possibilitaram a gente organizar esse evento, né, que se dispuseram e realmente toma bastante tempo, é algo difícil, né? Bom, primeiramente eu gostaria de agradecer, né, nos nomes, né, da professora Alice, da professora Sabrina e do professor Viana, né, a os minicursos, né, que foram ofertados e a todos os palestrantes, né, professores palestrantes do nosso departamento e convidados, né, que fizeram as apresentações. E, em especial, então, agora a organização da escola, né? Então, eu gostaria de agradecer a professora Ana Costa, a professora Camila Oliveira, o professor Emerson Barbano e ao Tiago, que está aqui, né, por ter levado essa organização, né, mas também aos estudantes, né. Eu acho que a gente pode dar uma salva de palmas para o pessoal. E também aos estudantes, né, que possibilitaram fazer isso. Então, eu vou citar aqui o nome de alguns, se eu esquecer, vocês me lembrem aqui, tá? Mas gostaria de agradecer a Camila Unger, tá? O Jaderson Poli, a Luna Oliveira, também ao Marcelo Machado, Matheus Reuli, Johan Soares, Elis Lubachewski, não sei se é assim que fala, Lubachewski, o Elias Hung, tá? Que ajudaram, né, na organização. Então, muito obrigado a vocês, né, pelo suporte, né, que deram aí para a organização, tá? E também, né, um agradecimento, né, para o pessoal que participou aqui, né, a vocês, né, que foram importantes, né, que são, né, a finalidade, né, dessa escola, tá? Então, muito obrigado a todos, tá? E um bom carnaval para todo mundo aí, tá?
E para a gente poder finalizar, gostaria de chamar o coordenador da Sexta Escola de Verão de Curitiba, o professor Emerson Cristiano Barbano.
Muito bem, boa tarde, então, a todos e a todas. Quero iniciar parabenizando o professor Viana, né, pela homenagem. A Escola de Verão é um evento que está sendo regular no nosso programa de pós-graduação, e a gente decidiu esse ano iniciar, né, ter essa iniciativa de usar esse espaço, esse momento, para homenagear professores, assim como fizemos para a professora Alice, para o professor Viana, neste ano. O professor Viana, então, tem aproximadamente 35 anos aqui, mais de 35 anos, professor? 36 já. Quase 37 anos trabalhando aqui na Universidade Federal do Paraná. E como ele pretende se aposentar em breve, a gente não podia perder a oportunidade de homenageá-lo nesse evento. E como vocês puderam notar, o professor Viana é muito gentil, além de ser um pesquisador do mais alto nível. Eu sou formado no interior de São Paulo, na universidade, na USP, lá de São Carlos. E aí, quando eu encontro as pessoas de lá, às vezes eu menciono, estou trabalhando na UFPR agora. Eles falam, professor Viana é de lá, né? Eu falo, sim, professor Viana é de lá. Então, ele tem um reconhecimento, um prestígio na sociedade acadêmica, que faz a gente ter muito orgulho de dizer que ele é do nosso programa de pós-graduação, do nosso departamento de física. Então, assim como eu falei para a professora Alice, né, espero que pedimos, né, em nome da comissão organizadora, que receba como um gesto de reconhecimento por toda a contribuição para o departamento, para o programa de pós-graduação, para a Universidade Federal do Paraná como um todo. Assim como o professor Ginter fez, eu não posso deixar de agradecer as pessoas envolvidas, a comissão organizadora, a professora Ana Cristina Sprott Costa não pôde estar aqui agora, que ela está numa banca de pós-graduação, mas ela ajudou imensamente na organização desse evento. Professora Camila Carla Queiroz Martins, Camila Carla Queiroz Martins de Oliveira, enfim, faltou um nome aí. Camila Carla Brits Martins Queiroz de Oliveira. Professor... Professor Tiago de Lima Prado também. Agradeço também aos discentes, né? Então, por exemplo, o Jaderson Poli, Luna Oliveira, que participaram de toda a transmissão, desde lá do Botânico até aqui, o Marcelo Machado, Matheus Royle, que ajudaram a conduzir os estudantes do Student Chapter durante as atividades desse evento. Então, agradeço, né, como o professor Ginter falou, a Elise e ao Elias, que ajudaram com o site. Todos os membros do FPR Autico Student Chapter, que é uma organização estudantil, que, como vocês perceberam, eles coordenaram várias atividades, desde do credenciamento, coffee break, fizeram o chair das sessões, coordenaram visita aos laboratórios, a confraternização de ontem. Então, uma equipe que o suporte deles foi fundamental para a realização desse evento. Agradeço também tem alunos da pós-graduação que se voluntariaram a nos ajudar, fizeram avaliação de pôster ontem, ajudaram no credenciamento também, então sou muito grato a todos vocês. Agradeço às instituições, então a gente teve o apoio do setor de ciências exatas, do programa de pós-graduação em física, do departamento de física, e, obrigatoriamente, eu preciso agradecer aos nossos financiadores e apoiadores, a Sociedade Brasileira de Física, a SBF, nós tivemos apoio da PROEC, que é a Pró-Reitoria de Extensão em Cultura, e da CAPES, que é a Coordenação de Aperfeiçoamento do Pessoal do Nível Superior. Então, dito essas coisas, eu quero agradecer a vocês, especialmente, né, que vieram participar da escola. A gente teve uma audiência bastante representativa. Eu fiz uma anotação aqui, deixe-me ver, mas a gente tem, né, participantes de vários lugares, para citar alguns, obviamente, Curitiba e região metropolitana, mas também de Ponta Grossa, aqui do Paraná, pessoas de Laranjeiras do Sul, Paraná, Florianópolis, de Santa Catarina, Araranguá, Santa Taguatinga, Distrito Federal, Guará, Distrito Federal, São Paulo, capital, São Carlos, no interior de São Paulo, Oeiras, Piauí, inclusive com uma participação internacional, né, tivemos a presença de uma participante de Cochabamba, na Bolívia. Então, é um prestígio para a gente poder recebê-los aqui, espero que tenham gostado, né, da nossa escola, que tenham aproveitado, que a gente possa ter mostrado um pouco das nossas atividades, e que vocês considerem, então, realizar um curso de pós-graduação aqui, vão ser todos muito bem-vindos e todas muito bem-vindas. Muito obrigado. Ok. Vamos para um momento muito esperado agora, que é a parte da premiação dos melhores pôsteres. Então, depois da avaliação que houve ontem dos voluntários, aliás, agradeço, né, não só os estudantes de pós-graduação, mas também os professores que ajudaram, como o professor Cristiano, o professor Igor, que não está aqui, que ajudaram a fazer essas avaliações. E aí, depois de analisar as notas, a gente selecionou os 3 que pontuaram mais, e eu vou, então, agora chamar essas pessoas aqui na frente para que possam receber o nosso kit, que vai ser o prêmio da nossa Escola de Verão de Física de Curitiba. Posteriormente, também será enviado um certificado para esses que ganharam o prêmio. Muito bem. Então, gostaria de chamar aqui, em terceiro lugar, Mariela Iziki Jailita, da Universidade Mayor de Saint-Simon. Por favor. Vou pedir ao professor Ginter que entregue, então, para Mariela o prêmio, por favor. Muito obrigado. Pictures. Ok, em segundo lugar, chamo Luca Rodrigues Cunha, da UNB, Brasília. Peço, gentileza, professora Alice possa fazer a honra de entregar. Tá pesado o prêmio, tá? E, finalmente, em primeiro lugar, quero chamar Bruna Marcela Igol, da UFPR. Para a entrega do prêmio para a Bruna, chamo a representante do setor de Ciências Exatas, professora Camila Carla Brites Queiroz Martins de Oliveira. Acertei! Bom. Pessoal, eu vou fazer aqui umas últimas palavras, mas eu peço que vocês também aguardem após eu falar para que a gente possa fazer uma foto oficial do evento com todos aqui presentes, ok? Então, para encerrar, eu quero mais uma vez agradecer a presença de vocês, né? Foi uma honra recebê-los. Espero que tenha gostado do evento, tenha gostado da cidade, que para quem é de fora faça uma ótima viagem. Aproveitem o carnaval, obviamente, aproveitem o feriado da semana que vem, e podem contar com a gente, estaremos aqui à disposição, como já dissemos várias vezes, serão todos bem-vindos, caso queiram voltar para cá, ok? Muito obrigado a todos vocês, e até mais.